All right, physicists, hello. Welcome to our March 31st edition of Physics, remote edition. Thank you for letting me do this. Today is this one's Easter program. You can see she's very saintly. That's my 4-year-old daughter, Iris, and this is my 1-year-old daughter, Beatrix. And so if I seem tired, that is probably why. All right, so on to the business at hand. Okay, so you've seen this. You've seen this slide before. We've discussed how when we went to angular coordinates, it was good because every time you talk about a spinning object, the different points, every point on that object is spinning at a different linear speed, but you can describe them as having the same angular speed. And so we did this sort of substitution cipher where we did all of our x's we replaced with omegas, all of our v's we replaced with, our x's we replaced with thetas, v's we replaced with omegas, and a's we replaced with alphas. And what we did with that substitution cipher is that we were able to carry over all of our information about our constantly accelerated motion and do it now for acceleration around an axis. Okay, now then we practice our right-hand rule. So the direction the thing is spinning, your thumb is pointing in the direction that we, as a convention, label the direction of the angular velocity, or today we're going to use it as the angular momentum. And to find the kinetic energy of an object, we realized that a good way to do it is to add up the distance squared from the axis of each little piece of mass and then multiply it by the mass. And we called that the moment of inertia, and it allowed us to put the kinetic energy in terms of the in terms of the angular velocity rather than the linear velocity, right? So instead of having k equals 1/2 mv squared, that's kilograms meters squared over second squared. Well, if I have 1/2 omega squared, this is just radians squared over second squared. So I need a factor of meters squared, and that's where my I comes in. So your I has that meters squared in the r squared part of it, and then it has the mass here. So the mass is contained in that, and it also has the meter squared part in it. Okay, on Monday we did quite a bit. So we said, let's calculate that moment of inertia for a couple of different situations. So we did a bar, and we realized that the moment of inertia for a particular object doesn't just depend on the object, it depends on what point you're spinning that object around. So if you spin it around the end, you get one moment of inertia. If you spin it around the middle, you get a different moment of inertia. And it tells you, that moment of inertia tells you something about how mass is spread out within your object. If it's really spread out, you've got a bigger moment of inertia than if it's close to the rotational axis. Then we define the torque. So the idea was that if you have an object and you want to get it spinning, if you apply that force in the radial direction, you're not going to get any spinning. It only will start spinning if you put that force in a tangential direction. Okay, so what we did with the torque was, that was the component of the force that is in, so just to draw, let's say that we have this force at an angle. It's the component of that force that's along the direction of that spinning. So you use the sine of, I guess traditionally they use a different angle because theta we already used for the angular displacement of the disk. Okay, so F sine theta, and then times that times the R. So the R at which the force is applied. Okay, so that's the torque. And we can find a direction for the torque by using our right hand. Okay, so R cross F, and then our thumb is going to be pointing one direction or another. It's always going to be, the torque is always going to be perpendicular to F and R. And so if we think about this as a vector, the vector torque is changing the vector angular acceleration. Okay, so if you add up all the forces, and you in fact have to add up all the torques, that'll give you the way that this object is accelerating in tangentially. So it's doing angular acceleration this way. And so remember, Newton's second law was F equals ma in linear terms, and it's going to be torque equals I times alpha. So torque is like an angular force, I is like your angular mass, and alpha is like your angular acceleration. In fact, it is the angular acceleration. Okay, so once we did that, then we said, okay, once I know something about how my object accelerates, I can think about doing work on it. And so what we did was we used our work energy, we integrated the torque over an angle, and that gave you energy. And the rotational version of the work energy theorem is how much work you put into an object is how much its kinetic energy changes. So this is your kinetic energy final minus your kinetic energy initial equals the amount of work that you put in. And then we say, okay, well, we already thought about power in terms of this. Why not, we had P equals the amount of work put in per unit time. This has units of joules per second, which is a watt, not the same as that W. This is a unit watt. Okay, and instead, in the old way of writing this, we would have put it as force times V, but now we're going to have it as torque times angular velocity. And notice that this has units of energy over seconds. Here, force times V would be Newton meter. Newton meter is a joule over seconds. So that had units of watts. Here, it's a little bit tricky to realize, but torque actually has the same units, if you actually work everything out, as joules. Okay, so that's a little bit confusing, but I guess we have to roll with it. Okay, so what are we going to do today? We're going to discuss rolling as a mixture of rotation plus translation. Okay, so we're going to talk about how, if you have a wheel, it has some speed at the center of mass, but the different parts of the wheel are actually moving at different speeds. And then we're going to talk about how to represent this motion as the sum of the if you want to find out the kinetic energy of that rolling wheel, for instance, what you would do is it would be the energy of the rolling plus the energy of the movement. Okay, so that's a clever way to do it. It might not be apparent right now that that is so clever. Okay, and what else are we doing? Well, we learned how to write the work energy theorem in terms of angular coordinates. So today we're going to learn how to write the momentum conservation stuff in terms of angular coordinates. Okay, so that's our preview of our day. Now, I am aware that this is a lot. So let's go back first and look at a couple of our homework problems from Chapter 10. Okay, so I want us to move back a little bit and make sure that we understand the old stuff, and then we'll press on to the new stuff. Okay, so here's the old stuff. I asked you to get going on your Chapter 10 homework. It says the figure below shows three 0.100 kilogram particles. Okay, that's your M. Have been glued on a rod of length 6 centimeters and negligible mass. Okay, so this L is 0.06 meters. And you see how this is divided into 3, so I think it's safe to say, just looking at the picture, that if you divide 0.06 by 3, you're going to get 0.02 meters. So these are 2 centimeters apart. It says, if we remove one particle, that is 33% of the mass, by what percentage does the rotational inertia of the assembly begin around the rotation axis decrease when that removed particle is the innermost one or the outermost one? Okay, so all I'm trying to stress with this is, what do we mean by the rotational inertia? Well, it's this thing. You take the mass times the distance from the axis of rotation squared, and you add it up for every mass in your system. So for this one, for instance, I would go I equals, for my first mass, it would be mass, M, and the distance would be D squared. Okay, there's the squared in it. So that's for my contribution of my first mass. Then I add on the contribution of my next mass. So this one would be 2D away, so it would be M 2D squared plus. And then this one would be 3D away, so it would be M 3D squared. Now notice, because this is squared, this would actually be M times D squared. This would be 4M times D squared. This would be 9M times D squared. And so what they're asking is, how does that change if you take away this one, or if you take away that one? Now I hope you can see this is going to be a bigger contribution than that. If you take away some of the mass that's far away from your axis of rotation, that changes your rotational inertia a lot more than if you take away a mass that's close to the axis of rotation. Okay, and it wants you to find what the percent change is. Okay, that is going to be just your the absolute value of your, well, actually you don't worry about absolute value. It could be negative. It would be your final I minus your initial divided by your initial times 100. Okay, the times 100. So this is going to give you a number probably between 0 and 1, and then it will, if you use this formula, it will be negative because your final is smaller than your initial. And then if you times it by 100, that'll give it to you in terms of percent rather than a ratio. Okay, so that's an example of rotational inertia. Now let's do an example of torque. So it says you've got this body, it has these 3 different forces on it, and it asks you what the net torque is. So essentially what you're going to have to find is this torque, and that torque. Now the only thing I want to draw your attention to in this problem is that your torque is of course going to be R, so this is going to be RA, which they give you, times F, so that would be FA, which they give you, and then the phi here is not necessarily the angle they give you. So notice they have given you the wrong angle. The angle that you want is, if you translate this vector so that these two are like this, what's this angle? So you consider R is there, F is there. What's the angle between the two? And so for instance, for this one, your angle A would be 180 minus 135. Okay, so that's true for all of these. You have to correct the angle to make sure that you're looking at this angle rather than that angle. So this one, not that one. The other thing that you want to be aware of when you're doing this problem is the directional thing. Okay, so this is where we get our right hand out and see if we can do it. Remember, it's R cross F. So you put your first you put your fingers in the direction of R, and then you curl them around in the direction of F, and your thumb will be pointing out in the direction of the torque. So for A, it would be R cross F. This one looks to me like it would be out. So TA would be out of screen. Okay, do it again for TC, R cross F. It looks to me like this is also going to be out of screen. And then if you go R cross F for B, this one would be into your screen. Okay, so to find your net force, you're going to add up all of the ones coming out of your screen minus all the ones going into your screen, and there you go. Okay, well, sorry to belabor this, but I think it's worth our time just to make sure that we're not confused. This one has us look at a thin hoop with a radius of 1.2 meters rotating at 280 revolutions per minute. So the first thing that, of course, I see, revolutions per minute, that tells me that's an angular speed. That's my initial 280 revs per minute. As soon as I see that, I think, I have to do a unit conversion. So 1 minute, 60 seconds. 1 rev, 2 pi radians. And it says it must be brought to a stop in 15 seconds. So if your omega final is going to be 0 radians per second, and the amount of time that takes place in is 15 seconds. So it asks how much work must be done to stop it. Well, you get to use your work energy theorem. Here is your I. Your I is going to be mass, which you know, times r squared, which you know. So this times this squared will give you your moment of inertia. And your omega final, you know, so that's 0 minus I omega I initial. So we had to make sure we had that in the right units before we stuck it into the formula. And so our work that we get is going to be negative. And then for part B, it asks what is the required average power? Well, power is work divided by time. So once you find the work using this formula, you divide it by the time to get your part B. Okay, give it a shot. If you have problems with it, please email me. Okay, so that is our, wait a second. Ah, yes. Okay, so those of you who attended class in person on Monday, I promised you that I would do this on Wednesday. However, we're doing it virtually. So please skip to the end of Monday's video. I do this problem at the very end of Monday's video. The idea is that the kinetic energy of a rod that's rotating around its end gets transferred into the gravitational energy when it goes up. And so what's changed is that your center of mass has gone up by some height, and so what you do essentially is you take your kinetic energy down here, so 1/2 I omega max squared equals, and then it's equal to how much the center of mass of that rod has increased in height. So mg delta y of your center of mass. Okay, and then so it's having you calculate this, and then using that to calculate that. Okay, so if you were in class on Monday, please skip to the end of Monday's video where I do this problem. Okay, so today we want to cover quite a bit of new territory about rolling and angular momentum. Now, I want you to look at this diagram from your book because I think it is helpful. And what it's trying to establish is that the amount that my center of mass, the center of the circle, the distance that it covers per unit time is going to be the same as the distance that is rolled through the bottom of this. Okay? So that center of mass actually is going to move because it moves along always above that point on the pavement. It's going to just be omega times r. Okay, so that's not that, you know, that's probably what you guessed. If you were going to guess and you said, I gave you, okay, here's the angular speed, here's the radius of the object. Tell me how fast the bicycle wheel is going. Okay, you probably would have guessed this. But I do want to caution you that there are some dragons hiding in this territory. So the point of the wheel touching the ground has an instantaneous velocity of 0. It stops. Now, when I claim that, it might seem very weird, because clearly the top of the wheel is moving. How can it be that the bottom is not moving? Well, let's take a look at this. Okay, so here are two sort of visual proofs. Now, here's a photo of a rolling bike wheel, and you can notice if you have an exposure that's a little bit too long, what happens is that you get a very blurry top of the bike wheel and quite a sharp bottom. Why is that? Well, it's because the top is in fact moving faster than the bottom. So to investigate this a little bit more, there's a nice photo in your book where they take a long exposure and they put a light on just one part of the wheel. And they put also a light in the center. Now notice what's happening. This wheel is rolling at a steady rate. So you can imagine the orange light here progressing forward at a constant speed. On the other hand, look at what's happening with this red light. It's going. Okay, so it's going to look like it's bouncing. So there's something very weird going on here. Notice what's happening at this point. When it hits the pavement, it turns around. Okay, so it goes from going down to going up. And when it does that, it in fact has an instantaneous linear velocity of 0. So that's a very weird thing to wrap your brain around. Let's look at it again. How can we think about this in terms of vectors? Well, if you attached a little arrow on each point of this rolling wheel, one way to think about this is that this is an object that is purely rolling and its axis of rotation is right there. So this point, in an instantaneous sense, is not moving, and the top is moving fast. The middle is moving at the speed that this thing appears to be rolling. Okay, so that sounds like I'm engaging in some type of sophistry, and I might be lying to you. But take a look at this picture, and I think the second picture is going to be more helpful. All right, so if you think about the rotation of the bike wheel, okay, and you just spun a bike wheel that you were holding up like this, you would notice that the top was going one way and the bottom would be going the opposite way. However, the whole thing is being translated forward. And so if you do a vector sum of these, the vector sum of the top and the top, you would get 2 times the speed of the center of the wheel. The speed of the center of the wheel is just what it is. It's not moving in the just pure rotation sense. And then if you do a vector sum of this, the v of the center of mass of this translation and of the rotation, this plus that would give you 0. Very spooky. All right, but if you go through all the math, and all the details are in your book, the upshot of it is that if you want the kinetic energy of a smoothly rolling disc, okay, so this is one that's not slipping, and it's just smoothly rolling, and you can put that in terms of frictional forces and all the stuff that we've learned before. What it's going to be is the kinetic energy of rotation plus your regular old 1/2 mv squared. That is the mass of your total of your whole wheel. V is the speed that it's moving forward. So there's your kinetic energy of translation. Okay, so let's do a little bit of practice. It says, consider the drawing of a wheel that is rolling forward to the right. Okay, so the center of mass is going, the wheel is going this way, it's rolling along, and in constant contact with the ground below. At which of the points indicated is the magnitude of the linear velocity the greatest? Okay, well, here the magnitude of the linear velocity is 0. There, the magnitude of the linear velocity is v, and there it is 2v. Okay, so the point where we have the largest linear velocity is right at the top. Okay, and you can imagine that the linear velocity of these, it's going to be somewhere between. It's not going to be as big as this. It's not going to be as small as 0. Okay, let's do another quick example. I have sort of cheated by giving myself the answer. I didn't do this problem before class though, so let's hope I can verify it. Okay, so it says a 1 kilogram wheel, so our M is 1 kilogram, rolls along a horizontal surface with a speed of 6 meters per second. So V equals 6 meters per second. What is the total kinetic energy of the wheel? Okay, that was me having a moment of faithlessness where I thought to myself, did they give me enough information? But yes, of course they gave us enough information to do this. We need only to trust in it. Okay, so let's see. We have our kinetic energy which is going to be I 1/2 I omega squared plus 1/2 m v squared. Now I can see how I'm going to calculate this part. It's a little less clear right now how I'm going to get that. Well, let's see how we would do it. What is our I for a solid disk? Okay, I can calculate it using an integral, or I can just look it up. And for the sake of time here, I'm just going to look it up. So 1/2 m r squared. So that's my I. Now I need to put in something for my omega, and my omega is going to be my v of my center of mass divided by r, and it's squared. So here's 1/2 I omega squared plus 1/2 m v squared. Okay, so it looks to me I can take 1/2 times 1/2 would be 1/4 m r squared, and this is squared, so r squared. Those r squareds cancel out, so they didn't have to tell me the r. That was the little piece of the little doubt that I had that I needed to pause the video over. Okay, so this is 2/4 plus 1/4 is 3/4 mv squared. So it's going to be 3/4 times m is 1 kilogram. V squared is going to be 6 meters per second squared, so that's going to be 36 meters squared over second squared. Okay, that I'm going to cancel the 4 on the bottom, so divide top and bottom by 4, so that becomes 9, and kinetic energy is 3 times 9 is 27 joules. All right, pretty slick. Okay, so that's our first idea. If you have a rolling disk that's just smoothly rolling, if you add up the kinetic energy of rotation plus the kinetic energy of translation, that will give you the total kinetic energy of that object. Okay, now we would like to extend our ideas about momentum to the idea of angular momentum. Now, for a single particle, the angular momentum is a little tricky to define. It's going to be, so remember, for our linear momentum, it was a little easy to think about because the momentum is just in the same direction as the velocity. Okay, so if I have an object going this way, its momentum is also going that way. Okay, so no big deal. It's just scaled by how much mass it has. Bigger mass, bigger momentum. Angular momentum is a little trickier because if you remember, our angular velocity we've defined to be perpendicular to the direction of the actual disk spinning. Now, going through this and looking at the angular momentum of each individual particle is a little bit hard. So that's where you just like we did with our torque, you have an R cross P. So that's where you're taking the part of that P that's in the direction of perpendicular to the axis of rotation, and you're multiplying it by R. So in that way, there's something a little bit more confusing about this angular momentum definition. But it actually simplifies once you go to a solid rotating body. So that's where, instead of just adding up the momentum of the angular momentum of each little particle, which, if you have an R and a P, it's going to be pointing out perpendicular to both of those. It's a little bit easier to think about the momentum of a larger object, because then we can put it in terms of our L, I, and omega. Okay, so L is going to be I times omega. So L is the angular momentum of your whole object, Okay, what units does it have? It's got R cross P, so it's going to be meters times meters per second, or I should say kilogram meters per second. So P is the meters per meter, or sorry, kilograms times meters per second. Kilograms meters per second. So that's kilograms meters squared over seconds squared. Okay, this is your inertial rotational inertia. And this is your angular velocity. Okay, so L is pointing in the same direction as your angular velocity. So let's just practice that part quickly. Angular momentum of the Earth. Okay, so here's a picture of our Earth spinning happily around its axis. If we use our right hand rule, it asks, what is the direction of the Earth's orbital momentum, angular momentum as it spins about its axis? Well, you could go ahead and look up, if you wanted to find the Earth's orbital angular momentum, what would you do? You would look up what is the rotational inertia of a spinning ball. That's one of the ones that you're going to have on your list. And then you would take it times omega, so 2 pi per 24 hours. And if you want to find the direction of it, you're going to use your right hand rule. And if I'm looking at this, it appears to be pointing north. Okay, so why is that useful? Well, for one thing, it's useful because just the same way that we rewrote our F equals ma in terms of our linear momentum, so remember our linear momentum was mass times velocity, our Newton's second law then could be written in this kind of elegant way, where the net force was thought then, what is it doing? It's changing the momentum of the particle. Now we can also do this for our total system. And again, if you're thinking about all these individual particles, it's a little bit complicated to think about. But if you think about one spinning thing that has some L and some angular speed, then you think about, okay, how am I going to change that angular momentum? Well, you add a torque. Okay, so this object, for instance, it would have an angular momentum that's going out of the page, and if you wanted to get it to spin more quickly, you would put a force on it in this direction, and that would have a torque that was also pointing out of the page. Okay, so if you add up all the torques, remember torque is R times F. So R is the distance from the axis of rotation that you're applying it, times F times sine of the angle between R and F. So the amount of torque is going to tell you how much is your angular momentum changing per unit time. Okay, so this is essentially a rewrite of Newton's second law. Let's see how we can use that in a sort of a straightforward problem. It says a sanding disk with a rotational inertia of 1.2 times 10 to the minus third kilograms meters squared. Okay, so they give you I in the right units and everything. Is attached to an electric drill whose motor delivers a torque of magnitude 16 newtons times meter. Okay, they even gave us that in nice units. About a central axis of the disk. About that axis and with the torque applied for 33 milliseconds, So the amount of time is 0.033 seconds. Okay, you had to divide this by 1,000 to go from milliseconds to seconds. What is the magnitude of the angular momentum and the angular velocity of the disk? Okay, so what you're going to use is this. Okay, so if you have something like this, you can find your change in L for a constant torque. For a constant torque, this just becomes T equals delta L over delta T. On the other hand, if you want to think about integrating this constant over time, that's also okay. But your delta L is going to equal torque times delta T. So they give you the torque, they give you the time. You multiply these two together to get your angular momentum. So that's what part A is asking. It's assuming it starts out with no angular momentum. You've changed the angular momentum by adding torque. So that's part A. And then part B, if you know this is your, this is your L final, your final angular momentum, it says, what is your angular velocity of the disk? Well, if you know your angular momentum, it's going to be I times your angular velocity. And so once you have this, you just divide it by I, which, remember, they gave you that, to find your omega. Okay, so give that one a shot. I don't think that is a very hard example, but it might be helpful just to get the notation. Okay, so we've added a lot of notation. Here's our last piece of notation. In fact, this is the end of what we're going to cover for new stuff in rotational dynamics. There's more to be done, of course, but this is all we have time for this semester. Okay, so you'll remember that we did a whole bunch of problems where we had a couple of balls come in, they would bounce off each other or stick to each other or whatever, and then you'd have different balls with different velocities going out. And what we said was you add up the momentum of all the stuff going in, it equals the momentum of all the stuff going out. Now, the precondition for that was that we didn't have any external forces. All of the forces were just within the system, and so if one object pushed on another, you had that Newton's third law reaction force. So those forces in total would add to 0 because you're doing a vector sum. Now, we have a similar situation going on here with angular momentum, where if we have an isolated system, the initial angular momentum is the same as the final angular momentum. So let's see a couple of examples where this idea can help us to explain some everyday situations. So here's a good example. You have a local show-off bodybuilder, and he's going on his stool, and he holds his weights out like this. Okay? He gets himself spinning, and so he has some rotational angular, he's got some angular momentum. His I depends on how far these masses are spread out. And what he does that's interesting is that he moves these barbells in. And remember, I, it's the sum of all of your masses times r squared. So once those r squareds, once those get smaller, this I gets smaller. But if your total angular momentum stays the same, if I gets smaller, omega has to get bigger. So what happens? He moves these in. His moment of inertia overall of this system gets smaller, but the angular speed gets bigger. Okay, there are lots of interesting examples of this type of thing. For instance, here would be a diver. She starts out jumping off, and she's not spinning very fast, but then she tucks her body in. So essentially what she's doing there is she reduces her moment of inertia about her center of mass, and that causes her to spin more quickly, and then when she wants to go and go into the water, she can flatten her body back out. That increases her moment of inertia, decreases her rotational speed, and allows her to make that nice finish. Same idea here. You're spinning more slowly when you jump up, and then you tuck your body in and start to spin more quickly. Now, a classic example, and I will do this in class when we reconvene next Wednesday. Remember, we have Friday off and we have Monday off for Easter break. Is that suppose you have a guy holding a spinning wheel. Okay. Now, you can have momentum conservation in this case without really changing the moment of inertia. You're not changing the distribution. What he does is he takes this spinning wheel and he applies a force to turn the wheel over. And so initially this wheel is spinning and it will have angular momentum pointing up. And then as he applies a force, so he's putting energy into the system, he's converting from chemical energy to kinetic energy, that wheel is now upside down, so the angular momentum of the wheel is pointing this way, but the total momentum of the system has to be the same if there's no external forces. And so what you need is the L of the guy. His angular momentum has to be big in this direction because the direction because we got this thing. So essentially what happens is that he will start spinning on the wheel in the same direction as the wheel was originally turning, because the sum of this plus this as a vector sum has to be the same as your initial angular momentum. Okay, so I know that's a little bit confusing, but let's just do one quick homework example with this. And it says the rotational inertia of a collapsing spinning star drops to 1/3 of its initial value. Okay, so you start out with a star that has some moment of inertia, rotational inertia initial, some omega initial. Then the I final goes to 1/3 of your I initial. But if we have for this object so how would that happen? The way that would happen is that you have the gases and they come in and they start to gravitationally attract. Okay, so the gravitational energy of that cloud is spinning in, the gravitational potential energy is being transformed into kinetic energy. So it's falling in on itself. Now, if you have a conservation of angular momentum, what this means is that I initial times the angular momentum initial equals I final times the angular velocity final. So this is your L initial equals L final. This is angular momentum at the beginning is the same as the angular momentum at the end. But we said that the final angular final rotational inertia is only going to be 1/3 of this. So this is because the cloud is contracted. So I initial omega initial equals 1/3 I initial times omega final. So if we divide both sides, what we find is that omega initial, omega final, and so it asks us what is the ratio of the new kinetic energy to the initial kinetic energy. Well, my kinetic energy final is going to be 1/2 I final omega final squared, but that's going to be 1/2 I final is 1/3 I initial, and then omega final is going to be 3 omega initial squared. So this is 1/2, 1/3 times 3 times 3 would be 3 times 1/2 I initial I omega initial squared. So in fact, it asks what is the ratio of the new rotational kinetic energy to the initial rotational kinetic energy. It has increased by a factor of 3. And just to say it again, why is that? It's because you have your gravitational potential energy being transformed into kinetic energy, and in fact that kinetic energy is, you see it in the form of the stars spinning more quickly. So we see this all over the place. For instance, the reason that that many of the planets go in the same direction, we think of that as being related to conservation of angular momentum. You think about the Earth-Moon system, all of this stuff, there are lots of astronomical applications of this that are very interesting. Okay, but I've held you long enough. Let's just recap. What are the big ideas of today? Kinetic energy of a smoothly rotating object. You've got it moving fast at the top, less fast at the middle, not at all at the bottom. And we say this is the kinetic energy of that would be 1/2 I omega squared plus 1/2 m v squared, where this is, you're just thinking about this as pure rotation plus pure translation. Newton's second law can be put in terms of angular momentum, so we said that torque equals the change in angular momentum over time, where the angular momentum is I times omega for a spinning object. And if you don't have external forces, you have L initial equals L final. The initial angular momentum equals the final angular momentum, and that can explain things as diverse as why stars spin more quickly as they contract, to why, how figure skaters are able to pull off their cool spinning tricks. Okay, so thank you for watching, and I will see you 1 week from today. However, of course, I'll be around, so if you want to come in and talk about homework or work on anything like that, please feel free to drop by. I'll be around this afternoon. I'll be around tomorrow all day. And okay, so have a great Easter.